Hi, in this video we're going to look at a vectors application question. We're going to start by doing it using our vector projections, and then we're going to look at an alternate method because with application problems there's often different ways you can go about solving them. So we've got the question on the whiteboard. Let me read it. James and Jane are camping in the middle of an open field. In the morning, James walks 500 meters at a bearing of 30 degrees true, where he stops to read a book. So let's underline that part because that's important to the question. And he stops there. Later, Jane walks at a bearing of 75 degrees true to search for James. So we've got that. Determine the closest Jane could get to James. So we're looking for a distance. Determine what angle Jane would need to look at to see James at this point. So we've got quite a bit going on. When it comes to these types of questions, worded questions in general, really helpful strategy is to draw a diagram. So let's go ahead and do that. We've got some axes here. James walks 500 meters, 30 degrees true. So that's about there. This angle in here is 30 degrees. And the length of that vector is 500 meters. So distance and direction, that is our displacement, which we represent as the vector. So that's that first underline done. We've got that information already in there. And he stops at that point, right? So he's located at this dot. Later, Jane walks at a bearing of 75 degrees true to search for James. And it doesn't say that she stops, she just keeps walking. So let's draw that. So something like this. Something like that maybe. And we know that's a 75-degree angle from here. So that angle is 75 degrees, the big one, which means that this small angle down here is 15 degrees. Okay, so this is Jane's walking path, and this is James's walking path up here until he stops. Determine the closest Jane could get to James. So if we're visually looking at this, where is the closest point going to be? Well, we could have here to here. That's pretty long, so it's probably not that one. We could have here to here. The closest it's going to be, and this is a very common principle that you see in these types of questions and geometry questions in general, is that the closest point, the closest distance between a point up here and a line is perpendicular to the line. So we've got a perpendicular line in here. Doesn't make any sense to have that. It doesn't make any sense to have something over here. It's going to be perpendicular to the line. So we've done the second part of the question. Determine the closest Jane could get to James. So we're looking for the distance of that vector or the magnitude of that vector. Determine what angle Jane would need to look at to see James at this point. So if we draw in some axes, we're also looking for this angle here. So the true bearing that she would need to look at. So let's have a look at this question. Well, this vector here, and let me draw over the line. This vector here is, we've calculated this one before. This is the projection of A perpendicular to B, and that's what we need to find and work out the magnitude of that. The vector here is just the projection of A on B, the vector projection of A on B. So if we can work out these quantities, then we should be able to work out the distance by finding the magnitude. Then we can work out the angle. So our formula for vector projection, A on B. So firstly, I need to call this vector A and this vector B equals A cos theta. Magnitude of A cos theta. So that's the adjacent length. And then we are multiplying that by our B unit vector. So we're getting a B unit vector down here. We're scaling it up by that length. So we've already got the magnitude of A, which is entirely why I chose this formula, because this is what we've been given. It's given with magnitude and direction. Cos theta is the angle between the two vectors. So for this angle, we've got 75 minus 35. 75 minus 30, sorry, degrees. Now we've got our B hat. What's our B unit vector going to be? Well, we know this angle in here is 15 degrees. So my B unit vector is just going to be cos 15 sine 15. And the reason for that is that if I draw a unit circle, and we have, let's even draw a vector in here with an angle of 15 degrees. So that angle's 15 degrees there. Then the coordinates of this vector are going to be cos 15, that's going to be my x, and sine 15 is going to be my y. In the unit circle, the length of this vector is just 1, which is what our unit vector is. So we can say that our unit vector is just cos 15 sine 15. This equals, let's get some more space, erase this out. We've got 500 cos, this is going to break down into cos 45. We know cos 45 equals root 2 on 2. So we've got 500 times root 2 on 2, which is 250 root 2, cos 15 sine 15. So that's the exact value. Let's just get the approximation so that we don't have to deal with bulky things. 341.51 and 250 root 2 times sine 15, 91.51. Okay, so this is the projection of vector projection of A on B, which is this one here. Now, when we're calculating this one, we know that this vector plus this vector adds up to that vector there. So let's write that out over here. We know that the projection, vector projection of A perpendicular to B equals A equals, okay, so we know both of these vectors. A is given up here. We've got this angle from the positive x-axis is going to be 60 degrees. So we've got the vector A is just 500 cos 60, 500 sine 60, and we're minusing away the vector that we've already found. Pop that into our calculators. This over here is going to be exact values, but we don't need to worry about it because this is already approximate value. So we end up with negative 91.51 and $341.50. Okay, so that's our vector here. That's this vector. Now what we're trying to find is determine the closest Jane could get to James. So we've got this vector, we need to find the magnitude, and that will give us the distance that we're after. So the magnitude of A perpendicular to B let's see what that is. We get 353.55 meters. If we're looking for an angle, we are looking for an angle. Let's draw our picture. We've got -91 and 340, so we've got something like this. This is our angle. And so our theta is going to be opposite. And we get 75 degrees. So this is 75 degrees in here. That is equivalent. We want our true bearing because of the application style problem. We want all of that. So we've got, let's call that theta 1, 75 plus 270, which is 345 degrees true. And we have an answer to our question. So we can write a worded response. So, looking back at the question, really important when we have questions like this to draw diagrams so we can visualize what's going on. And that's why I've built up this geometric sort of intuition all of this time, because this is what it's for, right? Solving real world problems, finding what we need to find. Having said that, there are other ways that you can do questions. That's not the only math we know, right? So having a look at this question, I'm going to show you another way to do this particular one. It's not necessarily going to work for all the questions. It depends on the information you're given and what you're looking to find. So if we have a look at this triangle here, what bits of information do we have? And we know that's a right angle. We have the length of the hypotenuse. We have this internal angle, which is 75 minus 30, that's 45 degrees. And we want to know this side over here, right, which we can call x. There's a very simple way we can do that using our trig ratio. So we can say we've got sine theta equals opposite on hypotenuse. So x equals what's that? We get 353.55 meters. Let's just double check that was the same. Yep, we got the same thing here. So that works. Now we have to work out an angle. So looking at this picture, we've got, if I extend this out, let's make that a bit bigger. Extend this out here. Let's extend this out. I know that, and let's do a horizontal line in here as well. And this line is parallel to this line. So I know that this angle, let's call it alpha, I know that alpha equals 15 degrees. So it's the same as this one because of the F rule. We know this angle is a right angle because that's a straight line. So let's call that alpha 2. Alpha 1, sorry, we haven't labeled there. Alpha 1 equals 90 degrees because angles on a straight line add up to 180, which means we can work out this one here, let's call it alpha 2, for the same reasoning, right? All of these add up to 180. So alpha 2, because of this rule, which equals 75 degrees, we can then get our true bearing. The axes are starting to get a little bit messy, but let me draw them in. So these are our axes. This is 75 degrees. We want to know what that is. Let's call it alpha 3 equals 270 plus 75, which equals 345 degrees. And we get the same answer that we previously had. So you can see that this working is probably a little bit quicker. The vectors method was a little bit longer that we had to sort of go through. It doesn't mean one is better than the other. One is certainly shorter and takes less time to do. But as you do more and more of these problems, you'll start to gain a bit more flexibility in the approaches you take. Doesn't matter which approach you take unless it's specified in the question that you must do it a certain way. Not every question that's given will be easier to do using our sort of trig ratios. It just depends on the information given and what you need to find. So this was a video on vector applications involving vector projections. I hope you enjoyed it, and I'll see you for the next one. This video accompanies a worksheet series that aims to develop conceptual understanding with vectors. If you'd like to access the worksheet, click in the description below.